Hello there and welcome to this Crypto Quantique video presentation. Today what I'd like to cover is some of the challenges that we overcame in the development of our second generation PUF technology. First of all, let me introduce myself and Crypto Quantique. So my name is Chris Jones. I'm the Director of Applications here at Crypto Quantique, and we're a London-based company. There's about 30 employees of us, and we have expertise in cryptography, hardware, embedded firmware, cloud software, and of course quantum physics. We have two product families, and these are second generation commercial products which are tried and tested on different semiconductor nodes. So here we show some of our trusted partners and alliances. We are part of the RISC-V consortium, and recently we were chosen by Intel as part of their Root of Trust for the Pathfinder project. And our partnerships shown here are Renesas, Andes, Microchip, ST and Macronix. Let's have a look at Crypto Quantique technology. We have two product families. The QDID is the quantum-driven identity. This forms part of the hardware root of trust of a semiconductor device. If this device is integrated into a semiconductor, it provides you with unforgeable, tamper-proof, and impossible to counterfeit unique identity. It means that you don't have to inject cryptographic keys into your product. They're generated by the silicon structure itself. And unlike other first generation PUFs, our PUF provides multiple uncorrelated keys, which can be utilized for multiple applications and services. The second product family is a software security platform that is agnostic as to where it runs. It's called the QuarkLink, and it provides security from chip to your application. It also provides certificate authority status for your IoT ecosystem. And it can also support third-party roots of trust. This means that it can support semiconductor devices such as microcontrollers, system on chips, with alternative roots of trust that are not necessarily integrated with the QDID. What these two products allow our customers to do is make more secure IoT devices. It also makes them easy to use using our technology, and cheaper to manufacture because you don't need to trust third parties and you don't need to inject keys into your product. So far I've mentioned PUF several times. Here is an extract from Wikipedia that gives you an overview of what a PUF is. Basically it stands for Physical Unclonable Function. And we here at Crypto Quantique have developed what we call a second generation PUF. This is a PUF that is specifically been designed as a security peripheral. It's based on a quantum effect, which is the measurement of quantum tunneling currents. And here on the right you can see a graph which shows the actual quantum tunneling currents that we measure in our QDID. What this array does is actually create a unique identity for the actual semiconductor device that the QDID has been integrated into. And what does this actually mean? What it means is that you do not have to inject cryptographic keys into your semiconductor product to give it unique identity. The unique identity is extracted from the QDID. Every single device that has a QDID inside will have a unique identity. Let's now have a look at the fundamentals of the QDID that we're actually taking advantage of here at Crypto Quantique. In a CMOS process, and you have here a standard CMOS transistor, electrons can actually leak across this interface layer or the silicon oxide layer of the transistor. This has become more prevalent as line widths of semiconductor physics has become smaller and smaller. Variations in this gate oxide thickness actually cause variations in the quantum tunneling currents, and it is this aspect that we take advantage of here at Crypto Quantique. We have developed a high precision differential current measurement circuit which allows us to compare the thicknesses of adjacent transistor gates, which you can see here, and these transistors are arranged in an array here, what we call the quantum array. Thousands of transistor pairs make up this array, and they produce multiple keys, and these are unique to each chip. This technology has been proven on both 22 nanometer and 65-55 nanometer, with a 12 nanometer FinFET now under development. This technology has been developed into the QDID product. The main benefits of the QDID are that because the identity of the semiconductor device is embedded in the silicon structure of the QDID array, it means you do not have to inject cryptographic keys in order to give the device provable identity. Also, you do not have to store the actual fingerprint that you extract from the QDID array. You can extract it at any time using the differential circuit. Because you're not storing any secret keys in memory, it means the device is extremely difficult to hack. The technology only uses standard CMOS transistors. There is nothing exotic about the technology. Because it's actually reading quantum tunneling currents, it actually is immune to traditional side channel attacks because there is no photon emission and it's not sensitive to temperature. Because of the technology that we've developed, we've also ensured that there is a low error rate. And because the array is so large, it means you can actually extract multiple keys that are actually uncorrelated. It means you can use different keys for different applications. Now let's have a look at some of the implementation challenges that were put before us in the development of the QDID technology. So firstly, let's have a look at the effects on the environmental variation. Obviously the QDID has to perform across a wide temperature range, and temperature actually impacts on the entropy source, and it requires design techniques with the ability to identify and correct errors. So here you can see two charts. On the left side we've got the differential cell current, and you can see the variation of the cell current for different temperature ranges from -40 all the way up to 115 degrees. As CMOS technology scales down, the direct tunneling currents tend to actually rise due to the reduction of oxide thicknesses, and this happens down to approximately 1 nanometer region. Now the variations in the gate current can be verified to be partly due to trap-assisted tunneling, and this therefore means that it's subject to temperature variations. So you can see here on the chart on the right how you can have bit flips that occur over the whole temperature range. This is about 10%, very small percentage of the cells in our array. So while the majority, about 90% of the array, tend to show an increase in the absolute magnitude of the differential cell currents, some pairs of the twin transistors do tend to have mismatched temperature coefficients. So this results in the differential current occasionally swapping polarity across that temperature range. And these result in these bit flips for the minority of cells, and these are particularly for the smaller current mismatches. So here at Crypto Quantique, we developed techniques to overcome these variations in the technology over wide temperature range. So this means that the QDID PUF can provide you with unique immutable cryptographic keys across the full IoT operating temperature range. So let's have a look at what new sources of errors can be introduced when using these advanced technology nodes. As CMOS technology scales down, high K gates allow scaling to thinner oxides, but these introduce new defects, and these could impact the accurate sensing of the oxide variations. Random telegraph noise effects are temporal current fluctuations, and these are observed due to the capture and release of electrons in traps at the oxide silicon and high K dielectric oxide interfaces. So as you can see here in the diagram, this can impact drain current or gate leakage and can introduce time-varying bit flips. As the capture and release of electrons is statistically random, each cell experiences an uncorrelated telegraph noise perturbation. Also, at these advanced technology nodes, the effects of device aging become more significant. This obviously was a problem for the QDID team which we needed to solve. The primary degradation mechanisms of bias temperature instability can also introduce differential current mismatches, which of course is exactly what we don't need with our technology. These exacerbate the random telegraph noise amplitudes and cause bit flips. Also, hot carrier injection can impact the drain source leakage, and time-dependent dielectric breakdown effects show up with these higher gate bias voltages. Electromigration is less of a concern for our low-power IP technology. Here at Crypto Quantique, we've identified and verified various design and system techniques to identify and resolve these sources of error. Our QDID depends on the device fabric and is closely tied to the manufacturing tolerances of the host semiconductor device. Therefore, the architecture solutions must be adaptable to different foundries, technology nodes, and new sources of perturbation in these advanced nodes. So our QDID PUF addresses various technology challenges through innovative design and system solutions. Let's now have a look at the system challenges that were actually presented to the QDID development team. Here on the right you can see a diagram which highlights the evaluation criteria that we needed to consider during the QDID development. So we needed to look at things like reliability, of course, how reliable was the device throughout its entire life and over temperature range, the entropy of the actual seeds being generated, the chip area, of course, which needed to be considered due to costs, helper data, how much helper data needed to be generated to ensure that the device was reliable, and then runtime, things such as power usage and latency. So let's have a look at the evaluation criteria in a little bit more detail. Because the actual source of entropy is quantum in nature from the QDID device, we need fuzzy extractors in order to generate secret keys from these actual quantum derived values. Error correction schemes can actually be coupled with system techniques to improve the raw reliability of the QDID itself and the generation of those cryptographic keys. The QDID actually passes NIST SP800, 22 and 90B standards, which cover randomness and entropy, so the device has been validated from that viewpoint. The actual uniqueness of each QDID has been characterized by inter-chip and intra-chip Hamming weight distributions, which again we have lots of test data for. Overall, from a root of trust implementation viewpoint, the QDID has been designed to be implicitly secure against side channel attacks. Attacks such as photon emission attacks, glitch attacks, and temperature attacks. A 3-month study was actually conducted by a third-party company called eShard, and they independently tested the QDID and concluded that it was highly resistant to side channel attacks, and this is required for EAL4+ certification. Let's now look at another challenge that was put before the QDID development team, which they solved by developing an automated process. The QDID is an analog block by nature, and it is dependent on the analog properties of the process that we are targeting. So we have many customers who want the QDID to be integrated onto different nodes. So we have to rapidly evaluate these new processes. We do that by taking the process design kits for these processes, and we actually analyze them and simulate them to ensure that the QDID can actually be integrated onto that particular node. The usual evaluation flow can be very slow and it is very work intensive. So the QDID team developed an automated tool to speed up the process. So let's have a look at this diagram to show you how the automated tool improved the process. So when we're looking at a new node, we actually have to take the foundry information and the device corner temperatures, and then we have to manually create test benches and simulation results for that particular node. The output data is then analyzed and then reprocessed through the test benches. So you can see here there's quite an intensive manual processing flow here, how many times this goes round and round until we get the results that we're looking for. The output of this is a summary report, and that gives us an indication of the work effort needed to port the QDID onto that particular process. So what we did in the automation side is we took the same data, but we created an input file. that was formatted in preparation for importing into our PDK evaluation tool. Now this is the tool that we developed, and it takes that input file and it analyzes it and does all the processing of simulating, exporting results and setting up test benches and outputting a summary report. So here we have the automated flow. Let's now have a look under the hood of the PDK processing tool. So here you can see we have the input file, and this is a text input file listing all the devices, parameters and corner combinations that we would actually like to see from the process. We then run a script written in Cadence Skill, and this ingests this list and runs the required simulations. The results databases are sorted and converted to ASCII for easier processing. What we then did is we wrote a Python script which is fully automated and can be set to run overnight or over the weekend. This script is then used to process the PSF files and generate a series of tables and plots with relevant information and write these in a LaTeX compatible format, which you can see here. Finally, we then simply run the LaTeX and a PDF summary of each of the devices is generated for easy consumption. This report, it contains information such as threshold voltages, transistor currents, noise versus dimensions, bias voltages, temperatures and corners. And what this provides us is enough information to provide our customers with a report on the performance of the QDID ported on the particular node that they're interested in. The major advantage of creating this automated evaluation tool is that we could reduce the time to evaluate a full PDK from 1 to 2 weeks down to 1 to 2 days. Now that you've seen some of the challenges put before the QDID development team, I'd now like to show you how the QDID is actually incorporated into an everyday IoT product. So now let's have a look at a typical IoT device journey. So here we have the QDID IP, which we've just been discussing. It is actually integrated into some kind of hardware device such as an ASIC, system on chip or a microcontroller. The QDID provides the hardware with a unique identity, and together with some cryptographic keys, that identity can be proven. This forms then the root of trust of the hardware. This hardware is typically integrated into some kind of IoT device. Because you have the root of trust with unique identity, it also means that you can actually provision the device at the bare metal stage securely. You can do this without having to trust any third parties, and this forms part of Crypto Quantique's zero trust philosophy. So with the provisioned device, you can then connect this device to the cloud service. This is typically assisted by another product from Crypto Quantique called the QuarkLink. The QuarkLink uses the QDID IP and the unique identity to allow secure onboarding of the device to a cloud service. A typical cloud service is someone like AWS or Azure. In the cloud, you would have your application that actually is running and using information from the device. The secure connection between the application and the hardware is through the unique identity of the QDID. Once this has been set up and the device is connected to the cloud, we can have certificate, exchange, device management, all part of the QuarkLink product that is provided by Crypto Quantique. So here you can see, in combination with the quantum-driven PUF that's integrated into your hardware and the QuarkLink IoT device management platform, Crypto Quantique can provide you with a secure connection of your IoT device to your cloud application. Using the QDID and QuarkLink products from Crypto Quantique, customers can build their IoT products with zero trust supply chain assurance, and also ensure that the security of their IoT device is managed throughout its lifecycle. In summary, QDID is a quantum-driven second-generation PUF, which provides a hardware device with the basis for a hardware root of trust. What this means is that the device will have a unique identity which is based on the silicon structure of the individual die that holds the QDID. QDID has been designed in consideration of the technology targeted, environmental and aging effects to ensure that the QDID is reliable throughout its life cycle. By developing custom automated tools, the QDID's performance can be quickly evaluated in each new PDK presented to Crypto Quantique by our customers. QDID is the first step in Crypto Quantique's end-to-end IoT security solution. Thank you so much for listening to this video presentation. If you require any further information, please visit our website at www.cryptoquantique.com.